We're now going to turn our attention to two important trigonometric limits. Like you might think, why are we going back to limits when we're getting through our rules? Well, we're at a point now where, as far as differentiation is concerned, what's left is we have to work on finding the derivative of other types of functions. For instance, trigonometric functions. We currently don't know how to find those derivatives, right? We can find derivatives of certain types of polynomials and algebraic functions, rational functions, and we have one basic exponential function that we can differentiate, and that's pretty good, but that's not sufficient, right? We want to be able to differentiate every type of function that we've been exposed to prior to starting our journey through calculus, right? So next up, we're going to look at trigonometric functions, but in order for us to figure those out, we need to establish a couple key limits, right? And the first limit is this one. The limit as x approaches 0 of the sine of x over x, right? And again, if we try to, the limit of the numerator is 0, the limit of the denominator is 0, so we do have an indeterminate form, right? But unlike the other indeterminate forms that we've seen up to this point, this indeterminate form cannot be reduced or somehow converted into something that makes sense simply by using algebra, right? I mean, there's no sort of factoring I can do here. There's nothing that I can do that worked previously that's going to work now, right? So we have to change our approach. Well, what is that approach? Well, what we're going to do is we're going to rely on a little bit of geometry and a little bit of trigonometry, right? Or maybe a lot, depending on how you see it. So I'm going to draw my unit circle. Right, so there's my unit circle. And we know the equation of our unit circle. It is x squared plus y squared equals 1 squared. So we know the radius is 1 and the center is at the origin. Right, so let's draw some stuff there. There we go. And then what I'm going to do is I'm going to make a sector in the first quadrant. So I'm going to make a sector in the first quadrant there. But then I'm also going to form a triangle here. So there's going to be a triangle there, right? And then we have a sector that has a little bit extra area there. And then finally, I'm going to look at a slightly bigger triangle that goes outside of the sector and then comes down here, right? So we have two triangles and a sector, and what we're going to try to do is to try to figure out the area of each of these, right? So let's say I start with the smaller triangle. So because this is the unit circle, this length here is the radius, which is 1, as is this length here, that's also 1. And then I'm going to call this x. I'm just going to label it x to represent my angle. So if I draw that triangle over here, I don't want to draw too much on this, otherwise it will get pretty messy. But if I draw that triangle, what I have is a triangle where I know the angle between two sides, and we have a formula from trig that allows me to find the area, right? And the area of this triangle is 1/2 times this length times this length times the sine of the angle, right? So it's 1/2 of 1 times the sine of x. So the area of that triangle just ends up being 1/2 times the sine of x, right? Okay, now what about the sector? So let me draw the sector, which is like a little slice of pizza. So it's interesting. It's just that it has this curved boundary to it, right? This is still 1, this is still 1, this is x. Now again, there is a result from trig that you might remember about the area of a sector. But if you think about it this way, the easiest way to think about it, the full unit circle has area pi, right? So the area of the unit circle would be pi times the radius squared, but since the radius is 1, the area of the full circle just ends up being pi. And what we've done is we've essentially taken out a portion of this pizza pie. Well, what portion have we taken? Well, the full pizza pie has 2 pi radians, and we've taken out the sector that's comprised of x radians. So the area of this sector is the full area, which is pi, times the fraction x over 2 pi, right? Again, the x here represents the angle. The full revolution in our unit circle is comprised of 2 pi radians. This sector is only comprised of x radians, so this is essentially the fraction of the whole whose area we're computing. So what does that come out to be? Well, the pi in this numerator reduces with the pi in this denominator, and all I'm left with is 1/2 x, right? And there is a formula from trig that if you remember that formula, I'm not going to state it, but there's a formula that we could have gotten this result from as well. But it's nice to think of that sector as just a certain fraction of the whole, right? Okay, good. So 2 out of 3, we need one more. And now what we're going to do is look at this big right triangle. So the one where the height of the triangle extends out, and then this hypotenuse here is out, right? Well, we know the base of the triangle has length 1, right? The question is, what is the length of this side, right? Well, let's see. If you think about it, this side of the triangle, it is in relation, with regards to this angle, it's the opposite side, right? And we know that this side is this would be the adjacent, so we have to think what trigonometric ratio involves the adjacent side and the opposite side. That would be tangent. So for instance, if I call this, let me just call this another letter, let me call this Z, then what I know, since I have a right triangle here, in fact, let me draw that one here, right? So we have this angle, X. We know that again, which is the radius of my unit circle, is 1, and I'm going to call this unknown height Z. But what we know is that the tangent of X is the opposite divided by the adjacent. So that means Z, right, is actually the tangent of X, right? So this is actually the tangent of X. And then because I have a right triangle, I know the length of the base, I know the length of the height. I can use the formula for the area of a right triangle. So this area, right? So let's call this area 1, let's call this one area 2, and let's call this one area 3, so that we're not using the same symbol to represent different areas. So then area 3 is 1/2 times the base, which is 1, times the height, which is the tangent of X. All right. Okay, so what can we do with these 3 areas? Well, what we can say for sure is that A1, the area of the smaller triangle, is definitely less than the area of the sector, which is in turn less than the area of the bigger triangle, right? So since, let's write that down. So since A1 is less than A2, which is in turn less than A3, we have this nice inequality. We have that 1/2 sine of x is less than 1/2 x, which is in turn less than 1/2 the tangent of x, right? And the only assumption here we're making is that x is somewhere between 0 and pi over 2 because we're in the first quadrant, right? So this is for these values of x, all right? Well, okay, so they all have a 1/2. So if we divide all three parts of this compound inequality by 1/2, we're going to get the sine of x, which is less than x, which is in turn less than the tangent of x. Now what I'm going to do is, now I have a definition for tangent. Tangent is sine over cosine. So this is what I'm going to do. I am going to say that the sine of x is less than x, which is in turn less than, so write tangent as the sine of x over the cosine of x, right? And as long as x is in this range, right, none of these ratios that are involved are 0, right? As long as x is strictly between 0 and pi over 2, none of these quantities are 0, right? So what I can do is I can actually take the reciprocal of all of these, right? Now if I take the reciprocal, what happens is I have 1 over the sine of x, and now this flips to become greater than, like that. And then I have to take the reciprocal of what's in the middle. I have 1 over x, that looks like that. And then this also flips, I get greater than, and then take the reciprocal of this, I'll have the cosine of x over the sine of x, all right? Okay, so one more thing. Now, writing it this way, I can also write this inequality as the cosine of x over the sine of x is less than 1 over x, which is in turn less than 1 over the sine of x, right? So just essentially, instead of writing the inequality going this way, I can start it with this quantity, which is the smallest of the three quantities, and then write it in an increasing fashion. This way, it's in a decreasing fashion. This way, it's an increasing fashion. One more thing to do. Let's multiply now all three parts of this inequality by the sine of x. If I multiply this lesser part, I'll just be left with cosine, right? So we're going to have cosine of x. And then in the middle, when I multiply this by sine, I'll have the sine of x over x, which is, that's the limit that I'm trying to figure out, right? That's the one I'm trying to find. And then this one, if I multiply this by the sine of x, I'm just left with 1. And what we have now is an equality that looks something like what we've used for the squeeze theorem. So since I'm trying to find the limit of this middle function, right? And remember, this is the one that gave us that 0 over 0 before. But what we're now saying is that this function, right, as long as your x is between 0 and pi over 2, is always going to be between the cosine function and this constant function, right? So what does this mean? Well, I can use the squeeze theorem. If I take the limit of this as x approaches 0, so the limit as x approaches 0 of the cosine function is the cosine of 0, which is equal to 1, right? And then clearly this constant function, so the limit as x approaches 0 of that constant function, well, our limit property says that this is equal to 1, right? So the lower function approaches 1, the upper function approaches and in fact is equal to 1. So then the function that's stuck in the middle, so by the squeeze theorem, the limit as x approaches 0 of sine of x over x has to be equal to 1, right? Very remarkable result. So by the squeeze theorem, right? So by the squeeze theorem, the limit as x approaches 0 of sine of x over x is equal to 1, right? Chalk that down to some good old geometry and good old trig, all right? So that's our first one. So we figured that one out. The other one that we will need, it's another one where it's interesting the way it pops up. But the other important trigonometric limit that we need is this. The limit, again, it's something as as x approaches 0, and the function is 1 minus cosine of x over x. And again, if we try to take the limit of the numerator and the limit of the denominator, right, we're going to get that it's 1 minus the cosine of 0 at the top, and then we're going to get a 0 at the bottom, and we get our dreaded 0 over 0, which again it doesn't mean anything. We have no idea what this means, right? Right? Indeterminate means meaningless as far as we're concerned, right? So what could we do here? Do we have to go find another inequality and use the squeeze theorem? Well, it turns out we could, but this one, we can actually make use of this limit by doing a little bit of clever algebra on this one. So this one now, because we know this limit that I have here in blue, it gives me a way to work with this one. Let me show you what happens. Here, what we're going to do is multiply the top and the bottom by the conjugate of 1 minus cosine x. So we're going to take 1 minus cosine x over x and multiply the top and the bottom by the quantity 1 plus cosine x, right, like this. All right, so when that happens, well, let's see. So we have the limit as x approaches 0. Now, at the top is the difference of two squares. You can say that this is a minus b times a plus b. So when you expand this, you're going to end up with 1 minus cosine squared x over, and then at the bottom, you have the x and then the quantity 1 plus cosine of x, right? We do need a little bit of trig here, right? Going back to our unit circle, remember that the polar or trigonometric form of the equation for the unit circle leads us to this identity, that sine squared x plus cosine squared x is equal to 1. This is one of the fundamental identities from trigonometry. So this means if I subtract cosine squared x from both sides, it means that sine squared x is equal to 1 minus cosine squared x. Well, that means I can replace this numerator with sine squared x. All right, well, let's do that. Right? All right, so let's write that. So this limit is equal to this other limit. Right? It's still kind of indeterminate. Even if at this point you still just try to plug it in, you're still going to end up with this meaningless expression. Right? But we're getting it into a form that where it might look more complicated than the original, but this is what we can do. I can write this single fraction as the product of 3 separate fractions, and those separate fractions all have limits that are not indeterminate, which is really remarkable. If you think of this as a single fraction and you try to plug in your x equals 0, the top will be 0, the bottom will be 0. However, if you look at it from a slightly different perspective, so what I'm going to do is write the sine squared x as sine x times sine x. And I'm going to put it at the first factor, I'm going to put it over 1. The second factor, I'm going to have the sine of x over x, right? So that takes care of that x in the denominator. And then the third factor, I'm now going to put a 1 over the expression that we have in parentheses here, 1 plus cosine of x, right? So 1 plus cosine of x. All right? Okay. So how does this help? Well, the fact is, individually now, these functions have limits. So using our limit properties, the limit of this product, right, is the product of these limits. So we have the limit as x approaches 0 of sine of x. I'll put it over 1, which I don't have to, and then times the limit as x approaches 0 sine x over x, and then times the limit as x approaches 0 of 1 over 1 plus cosine of x, right? Well, let's see. As x approaches 0, the sine of x approaches 0 as well. So then we have 0 times. The middle one is the one that we proved earlier, that the limit as x approaches 0 of sine of x over x, that's equal to 1. And then times, what's this one? Now that I have a 1 plus cosine in the denominator, if I evaluate the denominator at x equals 0, I'll get a 2, right? So this whole function approaches 1/2, right? And that's what I said. So each of these, they have limits that are well defined. And that's why we can use our limit properties. And then the property says, well, I can multiply the value of these three limits, but because one of the factors approach 0, then the product approaches 0. So that is 0. All right. So I think these are two, these are two very important trig limits, and we were able to evaluate them using geometry and the squeeze theorem and algebra. But just in summary, right, let's just kind of summarize. Right, so to summarize, we have the limit as x approaches 0 of sine x over x, that's equal to 1. And then the limit as x approaches 0 of 1 minus cosine of x over x, that's equal to 0, right? I mean, two simple answers when you kind of look at it, right? But then these two are going to play a very significant role when we go back to now derivatives. And in fact, we're going to look at the derivatives of trigonometric functions. So why don't you just tune in right now, and I'll see you in the next video.